In this video we're going to explore sampling distributions in the central limit theorem. So sampling distribution is a probability distribution of a sample statistic, and it's formed when we take samples of a specific size repeatedly from a population. Now when we talk about the distribution of sample means, we're looking at a distribution that's created by collecting the means of each of the samples that we've been taking. And the mean of the sample means is going to be equal to the population mean. So that's makes life a little bit easier. But when we talk about the standard deviation of that sampling distribution, it's not the same. We actually have to take our standard deviation of our population and we divide it by the square root of the sample size. So that's a very important piece to pay attention to. So this all comes into play when we're really talking about the central limit theorem. Because with central limit theorem, we can have any distribution and we have a mean and we may have a standard deviation, but it can't give us a ton of information if we can't fit it into a specific distribution. But what we can do is if we continue to take samples from our distribution and those samples are greater than 30, what happens is that data starts to become approximately normal. So if we look at the sampling distribution of the means, instead of looking at the distribution as it is, we can start to apply some rules we know about normal distributions. However, also with this, the fact that if we know that the underlying population distribution is normally distributed, then any size of our size n will work for this. The big thing we have to pay attention to is that when we start talking about the sampling distributions of the means, we have to make sure that we're using the standard deviation of the sampling distribution, which is that divided by square root of n. So let's look at a couple problems here. Samples of 42 are drawn from a random population with mean of 19 and standard deviation of 2.75. And they want to know what is the probability that the mean of the sample is greater than 20. So we ask ourselves, okay, a couple different pieces here. First, to be CLT, we got to make sure that we're greater than 30. And then second, we want to make sure we're looking at the mean of the sampling distribution. Well, in this case, we're looking at samples of 42 and the mean of the samples. So yes, that would be a central limit theorem problem. Second one here. Samples of 9 are drawn from a normally distributed population. And they want to know what's the probability that the mean of the sample is between 42 and 50. Now, you may say, oh, that's only size 9. And we are still doing the mean of the sample. But the key part to remember here is the normally distributed. Once we see that, we know we can use central limit theorem. In this last example, a sample of 57 is drawn from a random population, and it was the probability that a randomly selected sample is less than 11. Now, the difference here is that we're not looking at the mean, we're looking at just one sampling of those 57 that were in the drawing. And because you're only looking at one randomly selected sample, or one person, you're no longer looking at the mean of the people or sample, then you can't use central limit theorem. So let's look at an example. So people who have Time Warner on average are paying $45 a month and $5 standard deviation. Random sample we're going to do of 64 bills are drawn, and we're going to find the mean of those. You want to know what's the mean, the standard error of the sampling distribution. So this may be what the actual distribution looks like, where some people are paying way higher and some are paying lower, and it's all over the place with the mean right there at 45. But when we start doing these random samples and looking at the means of the samples, we then know that our graph is going to become normally distributed. And that's because we have over 30 people in this distribution. So this means that our mean of our samples will be the same as the population mean, and then our standard deviation of the samples, we just got to remember take the square root of the sample size, which is 64, and that'll give us our standard deviation. Now say for some reason you need to find a z-score for a central limit theorem problem. We use the same method, where we're going to take, in this case, we're going to use the sample mean minus the population mean, and we divide that by the sampling standard deviation. So say in this case, we still have that same Time Warner problem, but the difference being that when we did the mean of our sampling distribution that we had in this case, it was $43. And we know, again, it's still 64, so just like our standard z-score problems we've done before, we take the sample we found, 43, we subtract the population, and we divide by the standard deviation of the sampling distribution in this case. And it gets about negative 3.2. So that's way outside the normal range. Okay? The last thing, if we need to start finding probabilities within our central limit theorem, we use the exact same normal distribution formulas we used back when we talked about any typical sampling of that we know the underlying distribution is normal. The big difference is just paying attention that instead of using just the straight standard deviation, we use the standard deviation of the sampling distribution. In other words, we have to make sure we divide by the square root of n on our standard deviation. So say we're looking at U.S. teacher salaries is about $53,700, standard deviation of 11,000. Now if I start to take random samples of 36 teachers, and I want to know what's the probability that the average salary of the sample will be less than $51,000. So I know the value I'm looking at is 51,000. I know my mean is 53,700. What I have to pay attention to is my standard deviation. It's not just 11,000. It's going to be 11,000 divided by the square root of 36. So that's the very important piece right there. I plug it back in though, since I'm looking less than, that's just plugging straight into the normal distribution formula. And make sure you put it in the true. And it'll tell me that the probability is about 7%.